in Argentina, so we can start. So it's my pleasure to say to you hello once again. This is the last day of our session in differential equations and geometry. As in the previous days, for today we will have the talks of 4th grade mathematicians. And to start, is a big pleasure to me introduce to you Professora Svetlana Katok. Many of us have read her book and use it for our projects. But today, Professora Katok is with us to talk about rigidity and flexibility of entropies of boundary maps associated to Fuchsian groups. So, Professora Katok, very welcome.
Thank you very much for the invitation. It's really pity that this Congress is online, because I really wanted to come to Argentina. I've never been to Buenos Aires, especially. So, but anyway, so this is a joint work with my co-authors Adam Abrams and Ilya Garkovici, and it's about two very different results on boundary maps associated to Fuchsian groups. One is rigidity and the other is flexibility. So let me start with the background. You have a compact orientable hyperbolic surface of genus greater than or equal to 2. And then by uniformization, there exists a Fuchsian group, finitely generated of the first kind, which acts freely on the unit disk D, such that S is a quotient. And as the surface admits many possible fundamental domains. And so the one which is particularly convenient for our purposes is 8G-4 gonal fundamental domain. So topologically, it's actually very simple to see how you get exactly 8G-4, because all you need to do is to cut the surface with 2G geodesics that intersect in pairs. It's a necklace, sometimes called, and G of them go around the holes. There are G holes, and G go around the wastes. So this picture is for genus 2, and so you see that when you cut it out, then you get, in this case, you get a 12 gon, and in general, you get 8G-4 gon, sorry. And so the identification of the sites are exactly marked here. So 4 and 10, 3 and 5, etc. So this works for any genus by involution sigma by this simple formula. So sigma of k is 4G minus k if k is odd, and 2 minus k if k is even. And everything is going to be modulo 8G-4, of course. So the sites are identified, which identified k, site k and site sigma of k, they generate the group. So this is actually quite old result, which goes back to Dan, Fenchel, Nielsen, and Kobe, but it was particularly considered in this paper in the bulletin on 1991 by Adler and Plateau. Okay, now notice that F need not to be regular. It may be, but it doesn't have to be. So, but it satisfies two properties. The identified sites, of course, must have equal hyperbolic length, but also the angles at glued vertices k and sigma of k plus 1 add up to pi. So we call this 8G-4 gons, which satisfy this property, marked canonical polygons. In particular, the second property implies so-called extension condition. which is crucial for us. And this extension, it simply means that if you extend the sides of the polygon, they do not intersect the interiors of the tessellation, just like in this picture. Okay, so a marked canonical polygon is related to a regular AG minus foregone by famous Fenchel-Nielsen theorem. So for regular, the regular AG minus foregone is centered at the origin, and its all interior angles are equal to pi over 2. This is essentially Euler's formula. So Fenchel-Nielsen theorem tells us that if you have two surfaces, one obtained with regular and the other with irregular, then there exists an orientation preserving homeomorphism of the closed disk, which conjugate the groups. So if we denote S the boundary of the disk, then H restricted to the boundary is a homeomorphism of the boundary of the circle, preserving the order of the points. So these points, P's and Q's, are endpoints of the sides. Okay? And so basically the sides of the new polygon, if you have a regular polygon, then you apply H to regular polygon. And so each point, PK, is mapped to H of PK, and so with Q. And then if you connect the corresponding points with geodesics, then you get the new fundamental domain. So this is for the regular one, and then you look how H where H maps these endpoints, and you connect the endpoints, and you get a regular one. So actually, it's quite deep theorem, and it gives you some different feeling of the Teichmüller space. All right. So, and of course, if you have a marked canonical AG minus foregone and the associated Fuchsian group, which identify the size, then you can easily see that by Euler's formula, the genus is exactly G. Right. So this construction actually gives a less common representation of the Teichmüller space for genus greater than or equal to 2. It's the space of marked canonical AG minus foregones in D up to an isometry. Okay, so the topology is pretty clear. So the sequence of polygons PK converges to P if and only if the lengths of all sides converge and the measures of all angles converge. Okay, so this was done before for 4G gons, which is more standard representation of the fundamental domain. And so here are the references: Schmutz, Schaller, Zishang, and Thurston. So they talk about Teichmüller space as a space of marked polygon, but they didn't talk about AG minus foregons, which doesn't really make a big difference. All right. Now, the boundary map. So for each fundamental polygon, so you have these P's and Q's and points of the sides. And now let's choose a partition, such that AK is between PK and QK. So if I go back to this picture, so this is P1 and Q1. This is P2 and Q2. So A1 must be somewhere here, and A2 must be here. So you have flexibility. You can move from P to Q. Okay, right? Okay, so instead of just looking at these endpoints, P's or Q's, as was done before, it was suggested a few years ago, maybe now 10 years ago or more, by Don Zagier to actually consider this F sub A, where frankly, he was didn't even want to restrict AK between PK to QK. He wanted to basically take them arbitrary, just to see that the number is right. Well, this is still a conjecture, but we studied this situation when AK is between PK and QK. And we defined a boundary map, F sub A, which is equal to TK when X is between AK and AK plus 1. Okay, so now if all A's are P's, we get F sub P. And Adler and Flatot called it Bowen Series boundary map. Now, of course, this was considered by Bowen Series exactly. They used 4 J-sided polygons, but Adler and Flatot already considered AG minus 4 gons. Okay, and then of course you can look at FQ, but nobody considered FA before. Okay, so now this multi-parameter changes. Okay, suppose you start with the original polygon. As I said, it doesn't have to be regular. And then if you move in the Teichmüller space, then you change the polygon. But you also can change the partition. So there are 2 ways you can make a change. All right, and so this is just keep in mind. So when we talk about flexibility and rigidity, we are going to talk about these changes, change in the Teichmüller space, and also change of the parameter. Okay, so let me just give you some definition. A multi-parameter A is called extremal if for each k, AK is either PK or QK. Okay, of course. And it makes sense to look not P and Q, but some P's and some Q's. Now, if A is strictly between PK and QK, we say that it satisfies the cycle property if there exists integers MK and NK such that if you start with AK and you apply TK first and then some power of F, you'll get to the same point on the circle as if you apply TK minus 1 and then certain number of Fs. So this basically tells you that the map is not defined at the partition points, okay? So instead of saying, okay, well, that map is not defined, you can say, well, it is defined in 2 different ways, okay? So if you start applying, if you pretend that you are below, and if you pretend that you're a little bit above. The point is that the cycle property actually always satisfied if AK is between PK and QK. We proved that in some earlier papers, but it's not what I'm going to talk about right now, which is quite interesting. That no matter what AK you look, it always satisfies the cycle property. Now, if you have extremal, just like P or Q, you don't have a cycle property, but you get some kind of cyclicity. It's some kind of eventually periodic, okay? Because it's a kind of border case, okay? Now, if both MK and NK are equal to 1, then we say that A satisfies the short cycle property, okay? Okay, so now, So what I'm going to say is that if you look at this Fenchel-Nielsen homeomorphism, by the way it is working on the boundary, you see that these properties are preserved by Fenchel-Nielsen. So if you had for one polygon, for one fundamental polygon, you had this property that after conjugation, the property will be satisfied. This is not hard to see, just by definition, essentially. Now, each FA is a piecewise monotone, piecewise continuous map of the circle. Okay, well, it's a fractional linear transformation inside. Okay, but if you look how it works on the boundary, you can write down the formula exactly, and you see that it's piecewise monotone, piecewise continuous map. Okay, now if A is extremal or satisfies the short cycle property, then FA admits a unique smooth invariant ergodic measure related to Liouville measure. Okay, so we are going to use this. And now I'm ready to state the theorems. So the first, so the standing assumption is that S is a surface of genus greater than or equal to 2, and F is a point in the Teichmüller space. So with the surface, I also look at the fundamental domain, which is AG minus foregone. So the rigidity theorem says the following: it's rigidity of the topological entropy. So for any partition with AK between PK and QK, the map has the same topological entropy. This topological entropy does not depend on the partition, and it does not depend on the moving in the Teichmüller space. So you may ask, so are they, maybe they are topologically conjugate? No, they are not in general. But still, this rigidity of topological entropy holds. And the second result is about measure-theoretic entropy with respect to the smooth measure. And it has this flexibility property in the following sense. Okay. Now, unfortunately, we only can prove this if A is extremal or satisfies the short cycle property. And when I talk about the proof, you will see where the caveat, what we cannot do. Frankly, we think that this is true for all, but it's very difficult. All right, so this theorem consists of three parts. First part, so for any F, for any AG minus this canonical polygon, so measure-theoretic entropy is given by this interesting formula: pi multiplied by the area and divided by the perimeter of the fundamental domain. Okay. The second part is the maximal value of the entropy. This is a formula for it. It's achieved on the surface for which F is regular. That's something you probably would guess. And the third part is that for any H between 0 and maximum, there exists a fundamental, there exists a point in the Teichmüller space, or this polygon F, for which the entropy is equal to exactly H. Okay, so these two papers are actually accepted. One will appear in ergodic theory and dynamical systems, and the other in the book. Okay, so let me talk about a little bit about topological entropy. So usually originally topological entropy is defined for continuous maps, but Bowen's definition can be applied for piecewise continuous, piecewise monotone interval maps, and also can be extended to the circle maps. Okay, so this no problem with this. Secondly, Perry in 1966, he proved that a continuous piecewise monotone topologically transitive interval Markov map with topological entropy h greater than 0 is conjugate to a map of constant slope e to the h. And then Milner and Thurston, 1988, extended it to continuous non-Markov map, which was proved using the knitting theory. Alseda-Mezurevich extended it to piecewise continuous non-Markov maps. So we are going to use some kind of combination or some kind of extension of Alseda-Mezurevich for the circle map. All right. Okay. So let me start kind of explaining how the theorem 1 is proved. Okay. So first of all, as I mentioned before, all these boundary maps FA are piecewise continuous, piecewise monotone, and you see. So here, so you have P, say PK and Q, K. I mean. Yeah, this is P5 and this is P6. Okay, so between P5 and P6, you use T5. Okay, and this is a graph of T5. It's like fractional linear piece of fractional linear transformation, but not, because you look at the argument. You have to look at the argument. So you cannot say that this is really fractional linear transformation, but it totally behaves like it. So this is the result which we are going to use, which is a combination of Alseda-Mezurevich kind of extension for circle maps. For any A, the multi-parameter, there exists a locally increasing homeomorphism Psi sub A of the circle, which conjugates FA to a map with constant slope. Okay. And this Psi A, this conjugation is unique up to rotation. Okay, so FA, some of FA are Markov. For example, FP and FQ. But of course, most of them are not Markov. Okay, so how the proof goes? Well, first I want to, that's a kind of easy part. So Teichmüller deformation does not change the topological entropy. Why? Because after you apply H, you get something topologically conjugate. Okay, and this is essentially by definition of how H, if TK are side pairing transformation for F, then H inverse TKH are side pairing transformation of F regular. Okay, so so everything goes to the regular polygon. It's topologically conjugate. So in order to compute the topological entropy, you only need to look at regular. Okay, so for topological, it certainly is true. As you will see later, for measure-theoretical, this is certainly not true, because this H, it does something horrible to the measure. Okay, but for topological, entropy is good. Okay, so now for Markov cases, this is a standard. This is a standard thing. So you have, for example, P or Q or any extremal. Okay. So the image of PK and QK under the corresponding TK and TK plus 1 and TK minus 1, it's also end up in the same partition. So basically, if we look at all P's and Q's together, so if we divide the circle into 16G minus 8 pieces, okay? So then you get a Markov map, with respect to this alphabet, okay? And the corresponding matrix, it of course for each A, it will be different. So it Mij is equal to 1 if Fa of II contains Ij and 0 otherwise. This is again very standard. And the two matrices here are for P and for Q. And you will see that they are kind of look alike, but not exactly alike. And you cannot really see any symmetry. So there are the odd rows only contain 2 ones, and the even row contain 17, I guess, ones. And then they are all different, but some kind of similar, but different. And this is the same thing for any extremal. For any extremal, you can draw this. They will be. Now, the number of A admissible words of length A grows as lambda to the n, where lambda is this number, which only depends on genus, quadratic number. And therefore, the maximal eigenvalue of this matrix is exactly lambda. So this is true for any A. And this is kind of involved proof, but not very hard. It's not very hard. So therefore, topological entropy being the log of maximal eigenvalue is log lambda. So what do we know? So far, we know that for Markov cases, for this extremal only, the topological entropy is what we claim it was. Okay, so now look at this picture. So you have FP, for example, okay? And then for FP, you have the conjugacy, and this is linearization of FP, okay? Now, for FQ, it will be in general, it will be different. For each FA, it will be its own conjugacy, okay? So we did some experimentations, and we looked at these conjugacies, and they all look exactly the same. And so then we just started thinking how to prove that. All right, well, so for Markov cases, the conjugacy map can be obtained by standard means using Perry measure. Okay, and this is essentially goes to this 1966 Perry's paper. So it's constructed. So you have a Perry measure on the symbolic space, and then you have push forward of Perry measure on the circle using the symbolic coding map. And then you just define this transformation, this conjugacy as this push forward measure of interval from 0 to x. Okay, so this is a monotone increasing function. And the big result is that it actually, this conjugating function for P and Q, they are exactly the same. All right, so I'm not going to talk about the proof, it's very technical. So explicit formula, there is explicit formula for Perry measure, and also you have to look at the cylinder intervals for P and Q, and there is an interesting relation between them. So this is difficult, but it works. So what are the properties of this P? So we have CP and CQ, and then we will eventually prove that this CP, it will conjugate FA for all A. Okay, that's the goal. But what we it has periodicity property, and also it's symmetric with respect to the midpoint of each this point. Okay, so this is just zoom in of this point. We see there is a lot of symmetries here. So in order to prove that, that follows from this the theorem which I mentioned before. This follows from that, and I skip even not trying to prove. Okay, so now the crucial observation is actually quite interesting. That if you take this CP, this conjugation, and look what it does to each of this TK, okay, on the whole circle. The image is this strange kind of looking linear, fractional linear transformation, okay? So with two slopes. So slope lambda, it's in between these 2 points. This is a slope lambda, and this is a slope 1 over lambda. Okay, so this is, of course, this is very useful for us, and that also follows from this property of CP. Okay, and now what does it give us? Well, it gives us the following. It gives us that if AK is between PK and QK, okay, so SK is actually linear on a bigger interval. This bigger interval, it contains AK prime and AK plus 1 prime whenever AK are. Okay, so, and this slope lambda, this function is what, okay, so what you get when you conjugate FA with this particular CP, then you get a piecewise affine function with constant slope lambda, okay? And therefore, by Mezurevich and Schlenk applied to such map, the topological entropy is log lambda, okay? Any questions? So the essential part is actually this, and for because we have lambda on a bigger interval. Okay, so therefore the conjugation will be actually will satisfy this this function will be piecewise affine with constant slope lambda. Okay, and that implies that the topological entropy is lambda. As I said before, these maps are not necessarily topologically conjugate, which is actually follow from our early work, the combinatorial structure of these orbits, the cycle property. But these orbits may be very complicated. Some have several steps, the other will have one step, or anyway. So because, of course, the combinatorial structure is different, they cannot be topologically conjugate. Okay, okay. So I am trying to, I don't know if I have time, I want to talk about measure theoretical entropy now.
Yes, Professor Katok, don't worry. Yeah. You have still like almost 20 minutes.
Okay, all right. So let me explain. So let me recall that theorem 2 is about flexibility of the topological entropy of the measure theoretical entropy. Okay. So the first part is the entropy formula. Okay. So, and again, this is a condition which we cannot avoid. So we only consider the case when A is extremal or it has short cycle property. Of course, extremal, there are few extremal, there are finitely many extremals, essentially. Short cycle property is open condition. So we do have kind of big set, but it's not everything. Okay, so the formula which I'm going to prove is that the measure theoretical entropy is pi over area divided by perimeter. of the fundamental domain. Okay, so in order to explain how first of all how we get the measure, how we get the smooth measure, so I have to go to the natural extension of the map F. So you remember that map F was defined on the circle, and it was acting by TK when X is between AK and AK plus 1. And if you now look at S cross S minus diagonal, so you can define the map capital FA by looking where the W is. So my leading coordinate is W, not U. Okay, so this is the formula, and then you get the natural extension. So for Markov, from one side Markov, you get two-sided Markov. So this map was introduced in our paper in 2017, and it was shown that it has global attractor with finite rectangular structure. Okay, so that was a big thing. But again, conjecture is that it always has finite rectangular structure when A is between P and Q. We only can prove it for short cycles. And actually, Adam himself, he proved it for extremal as well. Okay. Now, so what are the steps in the proof of this entropy formula? Well, first of all, the smooth invariant measure. Well, the Liouville measure on the unit tangent bundle to the disk is given by this standard formula, which comes from the hyperbolic measure on the disk. It's invariant under the geodesic flow. There is another set of coordinates. Instead of x, y, and theta, we can look at u, w, and s, where s is the arc length along geodesic from u to w. So actually, I guess this even goes back to Hopf, if I'm not mistaken. We learned it from Adler and Flato. So for us, Adler and Flato was kind of Bible. Then this measure in this coordinate u, w, and s is related to this measure by a constant 1/2. Okay, so dm is d nu ds, and d nu is given by this formula. All right, so in this case, if we define it like this, then dm is 1/2 of the Liouville measure given by this formula. Okay, so this is a smooth measure on the space of oriented geodesics modeled as S cross S minus diagonal. Okay, and this measure is called sometimes geometric current. Now, both measures d nu and dm are preserved by Möbius transformations, and FA, which is the natural extension, it preserves the smooth probability measure. Geodesic flow is a special flow over a cross-section parameterized by omega A. And the first return to the cross-section corresponds exactly to the geodesic flow is a special flow over the cross-section, and the cross-section, there are many cross-sections, and the idea was to actually prove that each multi-parameter corresponds to a cross-section. Okay, well, so we can do it for short cycles and for the extreme. Now, FA is a factor of capital A projecting on the second coordinate. So so the smooth measure on the circle can be obtained as a projection of the measure. Okay, so this is essentially You take Liouville measure, you project on the cross section, and then you project to the second coordinate. So it's double projection. So this is what we are going to talk about, this measure. Okay. Now, formula for the entropy, how do we get the formula for the entropy? Well, I mean, it follows from Abramov's formula and Ambroska-Kutani. So this is very standard, used many times in the literature. In particular, we used it in 1919 paper, and it was used. We didn't invent it. Okay. Anyway, so the formula which follows from this Abramov and Ambroska-Kutani is the sum constant divided by the area of this attractor. Okay. Okay. So now we have the area of the fundamental domain on top, and we also have area of the attractor on the bottom. And now we have to explain how the perimeter comes into this game. Okay, now, well, this is area by, the numerator is the area of f by Gauss-Bonnet formula. So that's not a problem. The problem is the denominator, okay? So this follows from the following consideration. So in addition to this f sub a, which is natural extension map, there is also a geometric map which was considered by Adler and Flato. In geometric map, you just look at the geodesic and see what side of the fundamental domain it crosses, and you code it according to that. Okay, so the domain is defined like this. It's also a pair of point UW such that the geodesic intersects F. Okay, so this is a particular fundamental domain, and some geodesic intersect it, some geodesic don't intersect it. So you only look at geodesic which intersect it. Okay, and then if it exits through side K, then you apply TK to both coordinates. So the key correspondence between these two domains is the following, and it's clear from this picture. Well, I don't know if it's clear. There exists a bijection map between them, which is piecewise Möbius, and which maps these bulges. These guys are bulges, and these red things are corners. So it is identity everywhere else, and it maps bulges into corners. So we proved it for short cycles. Adler and Flato proved it for P. So the corollary, because it's piecewise Möbius, of course, the corollary is that they have the same area. And that's what we used. So if we can prove something like that in general for any A, that it would be the corollary will follow, but we don't know. In our case, it works. And now we use the lemma of Bonahan, which relates integral of this d nu, and you look at all geodesics which crosses this segment, and this integral is equal to the length of the segment. Okay, so this is how the integral of the geometric set omega g is related with the perimeter. Because geometric set, it consists of several kind of slices, 8g minus 4 slices, and each slice, gk, it's a geodesic which exits through side k, and by this formula, it can be interpreted exactly like this. And by Bonahan, this piece is the length of the side K, and when you add them all up, you get the perimeter. Okay, so this ends the proof of theorem 2, the first part. Okay, well, the second part is actually we call it isoareal equality, which is like isoperimetric equality backwards. And this is known result. We proved it. We proved it, but then we found the reference, which is like not so old, actually, 1997. I thought it should be done early before, but it says that if you have hyperbolic and gone, then there is the following inequality between perimeter square and the area. And this constant is just n tangent of whatever. So the exact, the equality achieved on the regular polygon. Okay, so this is in our case, f, Pn is f, n is equal to 8g minus 4, area is this, and it's constant in the Teichmüller space, when g is constant, and Ag in theorem 2 comes directly from the formula of the entropy, and this is the length of a single side of a regular polygon. And the last part, oh, I even have time. So flexibility of the entropy. So now recall that you have maximum, which is achieved on the regular one. And now you want to prove that any number between 0 and maximum is actually achieved on some, for some point in the Teichmüller space, okay? So now recall that Fenchel-Nielsen coordinates. I didn't use Fenchel-Nielsen coordinates before, but now we need to use decomposition of S into 2G minus 2 pairs of pairs. Actually, this is G equals 2. Sorry, we had picture in the paper we have for G equals 3, and then we decided that everything should be for G equals 2 in this. Okay, so now, so this is my old picture with 12 gone. Okay, and this is just you have 2 pairs of pens in this case. Okay, and the length of the geodesics, this independent geodesics, which are used for pairs of pens, they can be manipulated independently. Okay, all right. So what we do here, we actually take one of this geodesic from the necklace, which is used for, actually it's quite cheap trick. It's a cheap trick, but it works. All right, so since the length of this side can be made arbitrarily large, the perimeter can also be made arbitrarily large. Okay, so that means that this measure-theoretical entropy can be made arbitrarily small. Okay, and using the topology of Teichmüller space on this canonical AG minus 4 gone, we see that the perimeter varies continuously, and so essentially by intermediate value theorem, you can achieve any value from 0 and maximum. Oh, I have one more slide. So comparison of the entropy. Okay, so smooth measure is not measure of maximal entropy. Okay, so if A is extremal or has short cycles, the measure theoretical entropy is actually strictly less. Oops, that's it. This is not very difficult because we have formulas for one, and we have formulas for the other, and we just have to compare them. They are not. this is not measure of, smooth measure is not measure of maximal entropy, and you see the graph here, okay? And the regular, I take the regular because it's a maximal, but it's still, the topological entropy is still bigger, so the topological entropy is achieved on the measure which is not smooth. Okay. All right, I think, thank you very much.
Okay, thank you to Professor Katok. So before to say thank you, let us go with some questions.